right, so I'm going to in this video we are going to go through the Cubesat design specification. This document is from the Cal Poly Institute. They have their CDS or the Cubesat design specification. I'll call it CDS from this point onwards. That outlines the guidelines of anyone, any team, or any person trying to develop Cubesat. So it's gonna be a short video. We are going to skim through the document and pick up some parts of it. We are not going to go into a lot of details, but just trying to deconstruct what is necessary or rather required for the design. So this design covers the CubeSat levels from 1U to 12U. This is revision 14.1. So in case you are going through a different specification, just know that the one I'm using is revision 14.1 spec. Okay, so we have others, then you have the table of contents. They discuss several things starting with the specification itself, the string requirements, CubeSat dispenser, or rather the launch pad or the pod, depends on how you call it. So in the spec, they have the general specifications, the mechanical specs, the electrical specs, and the operational specs. Also, there's the testing requirements, because remember when you launch a CubeSat, it's a very high vibration environment. So when you're developing, you'd rather make sure that your CubeSat is designed to not fail at all. These are mission critical developments. So we need to have the least, not even the least, we should not have failure. In other words, that's why they are doing random vibrations, thermal vacuum breakout. I think they put the device in a vacuum chamber and I don't know, maybe tested the operation in zero air pressure. Shock testing, visual expansion, and then there's a philosophy for testing. Then you have the dispenser. The dispenser is the one that is used to, you see, when you launch like a CubeSat, it's a very small device, so it will take a very small footprint on the launch vehicle. So they need to have a way of launching it once it's in the desired orbit. So these small boards are designed that ensure you can stack up to maybe 3 or 4 CubeSats. Maybe let's say 1U size CubeSats, you can stack 4 of them. Once they are into the desired orbit, they are sprung out, and your CubeSat should be able to, as we'll see later, the CubeSat should be able to detect that separation switch. Yeah. So that's what they're calling the dispenser. Yep. Okay. So you have a list of acronyms and abbreviations here. Introduction. This is just a brief overview of the history. I don't have to go through this. Just shows the first models of CubeSats at Cal Poly CP1 and CP2 in 2006. Okay. So these are the sizes that the general sizes or standard sizes of CubeSats. We have the 1U, we have the 1.5, 2, 3, 6, and 12. U stands for CubeSat units. So if you look closely, you can see the rails here. The rails here are very important for interfacing with the dispenser, launch dispenser. So each of these sizes has its own rails. Yeah. So purpose of the purpose of this document, so CubeSat developers should maintain or should implement good engineering practice, test and verify their systems. The reason being that failure of CubeSats can damage the LV or primary payload, so putting the entire program in jeopardy. So remember, it's a ride share program, so you just hitch a ride on the a major mission. Maybe it's launching a bigger satellite or a space vehicle somewhere. Just hitch a ride. So you don't want to ruin the major mission. That's why you should ensure. That's why there are standards. In other words, right? So all participants have an obligation to ensure safe operation of their systems. Licensing is required by appropriate agencies and to meet the minimum design testing requirements outlined in this document. Right, that's cool. Mission requirements. Uh, the developer will be responsible for meeting the requirements provided by the launch provider. Right, the requirements in these documents are meant for preliminary design purposes. So, a launch provider basically, these are companies that allow you to get a lift on their space vehicle. So if they tell you do this and do that, you have to do it. Otherwise, you won't be on the same page. That's why they have written in bold that launch vehicle provider requirements supersede requirements in this document. All right. So what happens when we don't comply? Um, Other than compliance, we have to adhere to the launch provider's requirements. All right. Right. Okay. Definition of terms. So shall is very critical. It used to denote requirements that must be met. If you are told that something shall do this, it must do that. Okay. So should is it's a recommendation. Doesn't have to do it, but in many cases, failure to adhere to should statements will limit the opportunity. So these two words will help us during when you're reading the document. We will know which is a must to be done and which is like a recommendation, and but it's a good thing if we follow it. All right. Okay. So let's look at the first thing, which is the general specifications. General specifications. Let me highlight this a little bit for maybe later revision. Save it. All right. So all parts shall remain attached to the CubeSats during launch. Ideally, yeah, you don't want parts flying off. So pyrotechnics, I'll conform to this manual. I'll look at that later. And then any propulsion system shall be designed, interpreted, and tested in accordance with this volume 3. So basically, it means that if you have a propulsion system on a CubeSat, which is rare because CubeSats are small devices that don't need, manual propulsion. You can use things like reaction wheels or tokens to do that. Or to reorient in case of a detumbling situation in orbit. But in case you have a propulsion system, you should make sure you are to adhere to this AFSPC manual, I think. Page 91 to, I don't know, what is this? 91 to 710 volume 3. I'm not using propulsion system in my project, so yeah. FAA, low outgassing. I'm just skimming through these because I don't need them at the moment. Okay, so the magnetic field of any passive magnet shall be limited to 0.5 Gauss above Earth's magnetic field outside the CubeSat static envelope. So what I think this means, let me open the robot projects. Um, just a minute. Let it open this side. So this 2.1 defines how the magnetic field of the CubeSat should behave like. All right. So it means that just a minute. I create a new project. CDS revision 1. Okay. CDS revision 1. Let me just open this document. Just a minute. 21. Create. Okay, great. So I just want to sketch something here. So what this means is, I'll use an engineering paper here. What this means is that if you have a CubeSat, you have a CubeSat like this, and then I'll just draw a rough shape. So in case you're using magnetocast, it means the area of the bubble around this satellite should be, if measured, should be greater than 0.5 Gauss above the Earth magnetic field, so that you are able to reorient the spacecraft in case of any decoupling procedure. I think. Anyway, let's move on. The CubeSat should be designed to accommodate ascent venting per ventable volume by area of less than 50.8. I don't know what that means. Maybe I'll look at it later. So, mechanical specs. Mechanical specs. Wait a minute. The venting is like when you need to release pressure. So the ventable volume area of should be less than 50.8 meters. Okay. Mechanical specs. So these requirements are applicable for all dispensers. And then they go ahead and say the CubeSat shall use a coordinate system as defined in Appendix B. So Appendix B, let's look at Appendix B. Appendix, I think it's at the end of the document. Let me just go to the end of the document. Appendix B. Yeah, here it is. Appendix B. So they are saying that the axis should conform to this, whatever they have given here. So if you look closely, let's look for the axis. This is Z. This direction is Z positive. Z or Y positive. Then this is Y. I mean X positive. So the origin is somewhere at here on the corner. Okay, so if you look at this diagram, you can see this is the top. It's looking at us, at my face. So this is at the top, and this goes on for all the. This is the 1U. So if you go down here, 1.5U, they have the same um, axis orientation. So it's like this. Let me draw it on your pen. So it's like this. So this is X. This is what? This is Z and then Y. This is Y positive. This is Z positive. This is positive. Origin is here. Right. Cool. So let's go back to the first page. Let's go back. All right. So you are the mechanical specs. The standoff length dimension specified in the drawings on Appendix B exists to prevent interference with potential neighboring CubeSats and dispenser interfaces. So that means that the purpose of the standoff, basically the standoff is at the edge. At the edge here you have like further or an extended protrusion. So to prevent like those collisions with the neighboring CubeSats. Right. So extra volume, okay, tuna can. Okay. That depends on the dispenser launch or main launch dispenser basically. Okay. The Z phase of the CubeSat will be inserted first. Alright. No components on the yellow shaded sides. No components shall protrude further than 6.5 millimeters normal to the surface of the plane of the rail. Right? So it means like that in this on these faces, the allowed protrusion is up to 6.5 millimeters. So if you have like a GPS antenna or something, it has to be within that specific that distance. Deployables shall be constrained by the CubeSat, not the dispenser. Deployable, like if you have like a deployable solar panel that will stretch once you're in orbit, shall be constrained by the CubeSat. Rail shall have a minimum width of 8.5 millimeters measured from the edge of the rail to the first protrusion on each face. Okay, let's look at that. So this is 8.5 millimeters measured from the edge of the rail, this edge of the rail to the protrusion, the first protrusion on each face. So from this point to this point should be a minimum width of or minimum width of 8.5. All right, minimum. Surface roughness, that's surface roughness 0.6 micrometer. I think this to help. I think that is to help with the insertion of the CubeSat into the dispenser, launch dispenser. The edge of the rail shall be rounded to a radius of at least 1 millimeter. This is actually these specifications are very key. They come very key when we are designing the thermos. I mean the mechanical structure for the CubeSat. So remember in our first video we listed the parts of the subsystems of the project shadow flight subsystems. So when you are designing, you need to know what dimensions you need to use, and these specs are the final nail in the coffin in this case. But so when they tell you 1 millimeter radius, that's okay. The ends of the rails on the plus or minus Z have a minimum surface area of 6.5 by 6.5 millimeter contact with area with the neighboring CubeSats. Okay. This is more of the integration part. So maximum mass for each. So 1U is maximum of 2.0 kg, which is a lot in my case because we are carrying very few components. But masses larger than that, then the ones in the table shall be evaluated on a mission basis. Alright, so the CubeSat CUG shall fall within the range, which is here. So for 1U, it should be between this. So you are working in the negative. If you are working in the negative distances, negative 2 centimeters. We'll deconstruct this later, maybe in another video during design. The CubeSat structure should be made from aluminium alloy. So typically aluminium 70, 75, 60, 61, etc. are used for both the main CubeSat structure and the rails. If materials other than aluminium are used, the CubeSat developer should contact the launch provider or dispenser manufacturer. So maybe a company like EnduroSat, for example, if you need to use a different material, then you need to contact them. I mean, that's a no-brainer in my case. Yeah. So any aluminum CubeSat shall be hard anodized to prevent any cold welding within the dispenser. Cold welding happens when the materials are too cold and they like join. I think cold welding. Cold welding. Okay. Let's check about that. Cold welding. What is cold welding? Yeah, it's contact welding is a solid state in which training takes place without fusion or heating. So no heating or fusion. All right, contact welding basically requires literal no heat. So these methods can join even when they have not been heated. Anyway, so that's why they are anodized. If a CubeSat shares a dispenser with another CubeSat, each CubeSat shall employ a mechanism to encourage separation from neighbors within CubeSat within the dispenser, maybe a separator material or something. Mhm. Any mechanism that will provide separation is acceptable. Maybe a spring at the center or between the layers of the CubeSats. Okay. The most common placement of the CubeSat separation mechanism is centered on the end of the two standoffs on the CubeSat Z phase separation mechanism. Mostly the one that is mostly used is it's a springs, compressed springs. So when the launch pad is opened, they are just pushed out by tension forces, the compression forces. Deployment switches, these are electrical to know when you have deployed. Separation mechanism is right here in the corners. Okay, let's look at the next major thing, the electrical specifications. So electronic systems will be designed with the following safety features. These specifications are applicable for all dispensers. To prevent CubeSat from activating any powered function, the CubeSat power system shall be at power off state from the time of delivery to the LV through on-orbit deployment. So do I remember what LV is? This is page 14. So let's check the LV is the launch vehicle. Okay, yeah, launch vehicle makes sense. Launch vehicle. So it means shall be at power off state from the time of delivery to the launch vehicle through on-orbit deployment. So it means that during the whole journey, the CubeSat shall remain off, the battery shall remain off. What I think is that when the deployment is detected, that's when your systems come on, right? It means you won't be receiving data, during the launch period. All right, so CubeSat powered function include the variety of systems such as command and data handling, I think arrive communication, ADC, this is the altitude and determination control, deployable mechanism actuation, like the solar panels, you are deploying them or antennas. User power systems include all batteries, assemblies, and solar cells. Alright, powered on battery protection circuit may be permitted per specification 2.36. What does it say? CubeSat shall incorporate battery circuit protection for charging discharging to avoid unbalanced cell conditions. Alright. So then my next video will be designing the electronic power supply. So we'll go through this charging and discharging circuits. Additional manufacturer documentation and road testing will be required. Right, cool. Next is the CubeSat shall have at a minimum one deployment switch which is actuated while integrated in the dispenser. So this can be like a limit switch or a micro switch, can be something like a reed switch. There are many ways to do that. In the actuated state, the CubeSat deployment switch shall electrically disconnect the power system from the powered function. So if you're using a limit switch which can have the normally connected or normally closed or normally open. So when you activate it, it should be normally open. I mean, it should be open, right? So on the bench should be closed. Your systems are all on, but when you insert it into the dispenser and it's actuated, all the systems go off. That's what this means, right? So the deployment switch shall be in the actuated state at all times while integrating the dispenser. Right, cool. In the actuated state, the CubeSat deployment should be at or below the level of any external surfaces that interfaces with the dispenser or neighboring CubeSat. This ensures that the switch will not damage or interfere with the contacting surface. Okay. If the CubeSat deployment switch toggles from the actuated state and back, the satellite shall reset to a pre-launch state, clearing reset of transmission and deployable timers. Alright, I think this is more of a software implementation of a base state. It's like a reset. You reset it, does should not have memory in this stage. Yeah, real-time clocks may be permitted if they satisfy requirements 2.3.2.1. Okay, so real-time clocks. I'm using a lot of real-time clocks in my circuit, so they shall be isolated from the CubeSat's main power system, which means you can use like a coin cell battery. Frequency shall be less than 320 kilohertz. Okay, I'm using a 32.8, which is fine. RTC circuit shall be current limited to less than 10 milliamp. F pin is the remove before flight pin, and all CubeSat umbilical connectors shall be within the designated access port locations if available on the CubeSat dispenser. Right. So sometimes when you go to, I think maybe sometimes when you go to deliver that CubeSat to a launch provider, you still need to, what after it is inserted in the dispenser, you still need to like debug or check the health of your CubeSat. So they have these designated spaces where you can like connect wires and debug maybe USB cables, VGA, DC, whatever you're using. So they are saying in this spec that you make sure that whenever you have placed those, um, where is it? Wherever you have placed those umbilical connectors, it is within the designated access port locations. All right, cool. And they're saying some dispensers do not have access ports, therefore the RBF must be removed before insertion into the dispenser. Okay, removed before flight. It is advised that the Cubesat developer takes this possibility into account when designing the power on boot up sequence. Okay, so it means that RBF can be removed, during insertion into the dispenser or not. The CubeSat shall, which is a must, include an RBF pin which cuts the power, which cuts all the power to the satellite once it is inserted into the satellite. Correct? So so the purpose of the RBF pin is to, once it is inserted into satellite, it's like an off switch. So everything is off. If you remove it, everything comes on, right? Okay. It's like arming and disarming of missiles before fighter pilots fly. Yeah. So access to the CubeSat is not guaranteed during after or after integration. The RBF pin shall be removed from the CubeSat before integration into the dispenser if the dispenser does not have access ports. So there's a condition on to when the RBF pin shall be removed from the CubeSat. Okay, RBF pin shall protrude no more than 6.5 millimeters from the CubeSat tail surface when it's fully inserted. It is more of a mechanical thing. CubeSat shall incorporate battery circuit protection for charging and discharging, obviously, to avoid unbalanced cell conditions, additional manufacturer documentation. Right. The CubeSat shall have at least independent RF inhibit to prohibit inadvertent RF transmission. So these radio frequencies, basically. An inhibit is a physical device between a power source and a hazard. A timer is not considered an independent inhibit. Some launch vehicle providers will only require one or two independent inhibits depending on the CubeSat RF power output. Alright, so they need a physical device between a power source and a hazard. The CubeSat shall have at least three independent inhibits to prohibit the inadvertent release of any deployable structure, such as antennas or solar panels. Right? So you can do something like something to prevent unplanned release of deployable structures. I believe. Operational specs. So CubeSat will meet certain requirements pertaining to integration and operation to meet legal obligations. Operators shall obtain and provide documentation of proper licenses for use of radio frequencies. Alright. Amateur frequency use. This requires proof of frequency coordination by the organization. I shall comply with their country's radio license. I think for my case, this is a Kenya Space Agency that is required to provide this. I need to apply for this uh, license agreements restrictions. CubeSat mission design and hardware shall be in accordance with NPR to limit orbital debris. Any CubeSat component shall re-enter with energy less than 15 joules, I think, so that it can burn out in the atmosphere. Developers should be able to think, okay, these are just like regulations. Okay, NASA, ESA, debris assessment. Basically, they are trying to promote safe space use. Yeah. All deployables such as booms, antenna, solar panels shall wait to deploy a minimum of 30 minutes after Cubesat deployment. Which is activity dispenser detection. So minimum of 30 minutes. So it should not wait for longer than that. Cubesat shall not generate or transmit a signal earlier than 45 minutes after an on-orbit deployment. I want to ask why, but I don't know why that should happen. 45 minutes, maybe prevent interference with other Cubesats. I don't know, maybe. So it should wait for 45 minutes, and then that is when it should send maybe a put up signal to the ground station, probably. But the CubeSat shall be powered on immediately, can be powered on immediately following deployment on the dispenser, right? Non-US government entities under jurisdictional control of the United States will propose blah. Ah, the dispenser developer will conduct a minimum of 1 feet check-in with the CubeSat flight unit will be inspected and integrated in the dispenser or original dispenser to verify the fit. A final fit check can be conducted just prior to the integration of the CubeSat. This is just checking that the CubeSat can be integrated. Alright, cool. It is recommended to verify dimension limits using documentation specific to the intended dispenser in lieu of a document provided by the dispenser vendor. The CIFP located at this can be used. Alright, so I think that's cool. That's cool. Let's look at the technique testing requirements. Okay, so testing is like apart from the developing, testing is the next biggest thing you should do. So testing will be done to meet the launch provider's requirements, as well as any additional testing requirements deemed necessary to ensure safety of that. Okay, launch providers' requirements will supersede testing environments. Alright, cool. That has been established. Random vibration testing shall be performed to the levels and duration defined by the launch provider. Okay, so this is like just putting that CubeSat on a launch vibration table maybe and then shaking it as much as you can and test whether anything comes apart or if everything remains intact. Thermal breakout, thermal vacuum breakout shall be performed to ensure proper outgassing of the components. What is outgassing? It is when there is a pressure inside an enclosed thing and then it has to be released. Yeah, it's a release of a gas that was dissolved, trapped, frozen, or absorbed in some material. Oh yeah, no, it makes sense. If you ever looked at the ESP, I have an ESP here, you will see like there's a hole on the east side. There's a hole right there. The purpose of this hole is to outgas. I can use that word. Outgas during baking. So release any trapped air inside this module, the ESP that module during manufacturing. Shock testing. Shock testing shall be performed as defined by the launch provider. Shock testing is not typically required for CubeSats, alright. Visual inspection obviously shall be done to which are critical areas. Alright, then we have the testing philosophy. This section outlines a conservative test flow approach for CubeSats to meet the environmental test requirements for launch. CubeSat shall be subjected to either qualification or protoflight testing as defined in the CubeSat testing flow diagram. So the test levels and durations should be supplied by the launch provider, right? Okay, I think this like is more of like a test flow diagram of how the testing procedure should happen. All right. This will go. We'll go back. We'll go back to this later after we are done developing. Let's look at the dispenser lastly. So what is a dispenser? Basically, it's designed to carry the CubeSats and serve the interface between the CubeSat and the LV, right? There are several. The first system originally developed by the CPCL for the polypicosite light orbital deployer, PPOD. PPOD utilizes a real design. So I'll be using the PPOD for my project. The second system is a PSC. Utilizes a tab design and deploy a constraint mechanism, CSD flange, clamps onto these tabs, which creates a stiff invariant load path when integrated. Alright. Deployment forces a spring driving the internal pusher plate. Okay. Okay. So let me show you what that is. Pusher plate and the spring. So let's PPOD launcher images CubeSats. Yeah, so you see there's a spring inside here. Then there's this launch plate. This is the plate they are talking about. This plate right here. And it's pushed. Rather, it pushes the CubeSats out during deployment. Mechanical requirements are outlined. Okay, you've just gone through them. Developers are encouraged to explore both options to determine which is optimal for their needs. So mine, I'm a single developer here, but I've determined the people is the best for my case. Okay. To ensure safety and success of the mission, CubeSat will be compatible with, okay, will be, not a must, will be either compatible with either rail system or tab system dispensers. Because they have put diagrams to show, so if you look closer, you can see the access port. This one has an access port. Remember the one we said is used for umbilical debugging and cables and etc. And then there is the pusher plate, and then there's the rail pairs. All right. So this is a poly because it light deployer. It looks like that. Then the PSC looks like this. There's a tab. The CSD flange. I mean, both of them look fine. Depends on the one you choose. These are for 6U. For larger satellites, these are sort of U rail-based dispenser designed by Astrofane. Alright. Alright. So dispenser options. Dispenser specific options are available to support specific CubeSat mission requirements. So these are, of course, they will come from the dispenser provider. Okay. Alright, so we have a table here that shows the CubeSat dispenser options. Let's look at 1U. The 1U. It's funny, there's no max volume. Sorry, it's not. It's max volume that each of these dispensers can hold. So for example, the one I'm using, the Peapod Cal Poly, can hold a max of 33U, and it is the rail type, but does not have access ports. It does not have access ports. Does X mean? I think X means it's not available. Or is it? I don't know. Let's see. Let me infer from that. Oh, no, wait. Polypico satellite orbital deployer is this one, and it has an access port. So I think X means they have that feature. Yeah, they have an access feature. All right. Access ports are used to physically access the satellite where the CubeSat is integrated into the 6U dispenser. The access ports allow the RBF pins to be removed post integration into a 6U dispenser, okay, and they can be used to visually verify specification switch engagement after the CubeSat has been integrated. All right, cool. Additional mass, some dispensers have been designed to accommodate a larger payload mass. Okay, the tuner cans, etc. Power stroke data port. These options allows the CubeSat to electrically interface with the dispenser while integrated. So basically, the batteries can maintain their voltage levels during the launch period. I think, yeah. And then data port, basically, I don't know if I'm correct, but might help the launch provider know that the satellites are fine. They have been deployed, all of them, etc. Okay, right. So dispenser developer, I'll check that later. Contacts, all right. Cool. So I think that's all. Then we have the appendix B. This is more of a mechanical design thing. It's cool. Axis, first of all, you have to comply with the axis. Side X, side Z, side Y. This is for 1.5 U. You can see it's larger than 1 U. So I'm developing a 1 U, but yeah. So if I look at this, you can see that, wait a minute. So the minimum thickness of the rail is 8.5 millimeters. Is it millimeters? Yeah. Or dimensions in millimeters. All right. So obviously they cannot be in meters. So 8.5 millimeters. So this is 100, 100, 100 by 100 basically, by 100, 1U. My PCBs are 96 by 95. Yeah, they'll fit in. I'll do the changes later. So if this is 100 and then this is at 113.5, it means that 0.5 to 7 centimeters here. No, 7 millimeters. 0.5 to 7 millimeters. So that this becomes 7, which is 14. Then this is 100. That's 114. But I've told you this is 113.5. So this can be 6.5 and 6.5. Cool. Makes sense. 6.5 minimum, like the height. 6.5. What is this? Okay. Is the cross section area. But this is 8.5. So oh no, wait, this is from this part, not this one. So this 6.5 is at this point to this. So if from the edge to the edge is 8.5, 8.5 minus 6.5 is 2 millimeters. So this fillet is 1 millimeter radius. I remember there's a spec that says this should be 1 millimeter, the radius here. Right, cool. So that is repeated for 1U, 1.5, and the rest of the satellites. Yeah, as you can see, etc. All right, cool. So that's the CDS document, 34 pages of Cubesat design specification. So I think we're on the right track, and I'll leave a link for download for this document in case you want to go through it, and I'll see you in the next one. Have a good one.